I have a feeling now you can hear me. Good. I'm a bit humbled by all the previous presentations because they all knew where they were and where they were going. That is not the case for the Data Management Center, but there's a perfectly good explanation for that, which I hope to present to you now. I'm not here to rain on the parade of ESS, but as we hear, ESS has been on the way for 30 years, so has a lot of other mega science projects. So we're actually living in a decade of mega science projects. And we have at least 5 very, very large European science projects going on. And all of those have 2 things in common. First of all, they're very expensive. Secondly, they all produce huge amounts of data. So I've been asked to come here and talk a bit about how we handle very large data amounts in other experiments and how we foresee a data management center for ESS to be built and what kind of tasks it should do, and especially what makes ESS different, because as we heard the Swedish delegate say early on, this is also going to be for application and for industry, and that actually makes the whole data infrastructure very different from all the pure science projects. So we have ESS, and ESS is going to be big, at least locally, and it's going to be somewhat different from all the other mega science projects in that we are going to have industrial users. There are no plans for ESS Data Management Center as of now, primarily because we do not know what the ESS accelerator and instruments are going to look like. We would be pretty foolish to design data handling and storage and acquisition for a machine we don't know what looks like yet. So the Data Management Center has a set of visions, and the Data Management Center will have its own head, as Colin pointed out earlier on. But for now, there's a set of visions that says that it should provide seamless global access to the software and the data that will be handled by the Data Management Center. So this is important. This is a European project, and European researchers are going to work together with researchers outside of Europe, and everybody will need access to this Data Management Center. It will have to provide sufficient storage, computing power to allow the users to do what they want, that is to plan their experiment and to analyze the results afterwards. That's sort of an obvious statement that doesn't really survive the negation test, but still we want to make sure that you understand that we are committed to delivering what is needed. We will have to provide world-class data archiving, saving the data for a long time, and I'll get back to that because it's not nearly as simple and as trivial as it might sound. We're going to guarantee integrity and secrecy of the data, and this is what makes ESS completely different. If you go to CERN and say, oh, how do we make sure that your data is secret? They'll look at me and say, we don't want our data to be secret. Astronomers don't want their data to be secret. Most biologists don't want their data to be secret, but when AstraZeneca is going to do measurements in this thing, they want this data to be secret, at least until they have patented whatever should be patented. And we're going to have to worry about future technology. We do not know what a computer looks like, and I have a few examples of that at the very end. So first of all, users should be able to work on ESS with the Data Management Center from home. They're most welcome to come and sit with us at ESS, of course, but they should be able to work from wherever they call home. This is a common European installation and should not be requiring people to come to this region just to use the machine. And we're going to have a very broad user base, and this is something else that makes ESS different. It's not just a bunch of neutron physicists who know their software and are very happy with a shell to get access to a machine. There are going to be engineers and biologists and medical people, and they are used to shrink wrap software that is a lot more user-friendly than what we see in the neutron community today, and we have a challenge of developing new software that is actually user-friendly in this context. So this is, with a computer scientist perspective, what the Data Management Center is going to do. And I explicitly did not ask any neutron scientists about this workflow because they would add at least 100 other boxes to it. but I'm trying to keep it very simple here. We're going to simulate the experiment before we do it. Then we will actually go to Lund and put something into the machine, and neutrons will come out, and they will be acquired at the machine end, and the results will be sent to the data management center, where the user can then afterwards analyze the results and get the pretty pictures that we saw in the movie this morning. Obviously, things aren't quite that simple. You're going to do a lot of simulations before you go into the machine. It's going to be a very big machine. It's going to be a very attractive machine. You don't just put a sample in and have an image and see if it went well, and then try again tomorrow if it didn't. So you want to make sure that your experiment is optimal when you get beam time, which means that you will want to simulate a lot. So we will have to prepare for a lot of simulations. And actually, once you're all done, you're probably going to start all over, because you learn something new, and now you have to design a new experiment. Data archiving. I've spoken to a lot of people who knows a lot about neutrons, and they say, yes. Right now, we don't quite know how much time we're going to save data for. We don't have any tradition for it. So for now, the computer scientists in the field are just saying we probably have to store this data infinitely. The good thing about data is that relatively it becomes smaller and smaller, so it shouldn't be too expensive to do that. More importantly, if we're going to use the data in 50 years, we're going to have to know a lot about the machine and the state of the machine when this data was achieved. So we're going to spend a lot of time trying to figure out the metadata, and we're going to give input to a lot of the instrument designers for a lot of parameters that they might not have thought about reading out of the machine, because we want to be able to provide users with that information 50 years down the road when it turned out that, oops, temperature actually turned out to be important. Maybe you already know that, but something else that actually turned out to be important. So we're going to log a lot more, hopefully, than what you'd think of today. And then we don't know what the data is about. I've been pressing the best in the world, and they say, well, a petabyte is probably a lot. So if I press them to tens of petabytes per year, that's stretching the imagination of all the neutron scientists I've spoken with so far. Those of you who are not quite with us, a petabyte is 10 to the 15th bytes. It may sound like a lot. A petabyte is 1,000 of the largest hard disks you can go out and buy today. It's not a lot. And 10 of those is 10,000 very large hard drives today. In 2026, it's not going to be a lot. You'll probably have children, grandchildren that have PlayStations with petabyte disks at the time. So I'm not worried, is what I'm saying. This is going to be reasonably easy. I can tell you right now, we're doing this. So CERN is actually producing 13.5 petabytes of data per year. But that was the plan, but it turns out that the machine is a lot better than we thought it is, so it's producing 25% more data. Now we don't quite know where to put it, but we'll figure it out. So in the order of 15, 16 petabytes of data is not a problem in 2010, so it's not going to be a problem in 2025. And then we have the integrity. We need to make sure that the data doesn't change. That's, to the industrial part of the public, maybe uninteresting, but unfortunately, cheating has arrived into science also. And so the major journals actually require you to submit your raw data set when you make a publication in Nature or Science, you have to submit your raw data set. They're not going to be happy about a petabyte data set. So they will probably have to make contracts with the data management center saying we will ensure the integrity of this data. And more importantly, as I said, commercial users will require secrecy. And right now, when I talk to the few commercial users that are neutron sources, it's very simple. They use a rule called security by obscurity. Nobody else knows what we were looking at, so how can they make use of the data? Well, newsflash, we're getting very, very good at finding patterns in data we don't know what was anything about. Actually, it turns out we're better at finding patterns in data without assuming anything beforehand than we are when we assume stuff beforehand. So we are going to need real security measures for the pharmaceutical companies to be able to use this. So when we look into the future, I don't know what to say. Okay, I stand before you as a computer scientist, a computer architect. I've been doing this for 20 years. I don't know what this future looks like. I can tell you that for many years, when I worked at CERN and helped design systems there, we were assuming that Moore's law was going to hold up in the sense that every machine becomes twice as fast every 18 months. When I look upon the audience, most of you remember buying a new machine every year because it was half the speed of everybody else's, yes? Do you remember when it stopped? You realized it stopped, right? So we haven't actually had faster computers since 2004, when Intel announced that they were never going to make a 4 gigahertz Pentium 4. If they had, they would actually have ended up with a 16 gigahertz Pentium 4 in 2007, which would unfortunately have had a surface temperature of 6,000 degrees centigrade. That's the surface temperature of the sun, and it's really hard to find plastic to wrap chips in that. So we're not getting faster chips, we're getting more chips at the time, and that presents us with new challenges also. So I'm not going to tell you what a computer looks like in 15 years, because I've made that prediction once, I made it wrong, so let's just be sure that we don't make that mistake in the ESS. We're going to make all new spectacular mistakes, of course, but not this one. We don't know what storage is going to look like, but I can tell you that if you talk to anybody, they say, oh, it's going to be flash. Well, we still don't know the lifetime of flash. We know simulated lifetime says that it's not going to be a problem, but in reality, we don't know. So you know that a lot of public administration actually have problems right now because it turns out that the first laser printers, you can't read it after 10 years. The carbon dust falls off the paper after 10 years. So even paper doesn't work. So there are things to worry about here. And visualization is also going to be important. So after Avatar, I assume everything is going to be 3D. You will have 3D televisions in your living room a year from now, or you can have it at least. But from a scientific point of view, actually seeing a structure in 3D makes sense. So it's not just entertainment at this point. And as I said, we don't know what data analysis is going to look like, but it's probably going to be complex. So just to show you that we're not just posing questions, we are also preparing for it. So these are comparisons to conventional CPUs and the cell processor. This is the one in your PlayStation 3, if you have one of those at home. And the GPU, which is the graphics card on your machine. And these are ESS-type simulations that we can speed up a factor of 100 by moving on to a graphics card. But first of all, the data management center is actually going to help design the machine. So the machine will have to be designed, and including in that design is going to be a lot of simulation. And that's a good news. So we can't design the data management center before we know what the machine looks like, but the machine can't be designed without the data management center providing CPU cycles for the simulations. That's a good thing, because it's the same simulations that we're going to use at the end for simulating experiments. So we will get a very nice, slow startup with a very small user base that is highly skilled and knows exactly what kind of questions to ask and what kind of things to demand. And actually, work is already going on. So this is the month of February, and the amount of compute jobs, simulations that has been run by people not in Copenhagen, not exclusively in Copenhagen or the region, but from all over Europe that are sitting around doing experiments on designing the ESS instrument and the accelerator right now. And as you can see, sometimes they actually do think, and sometimes they work a lot. And this one, the 300, this is actually for today. So this was as of noon. So that might be a Heisenberg observation that they realized they started monitoring their work activity, and a lot more simulations were submitted this morning. But maybe yesterday, day before, somebody got a really good idea and started working. So that's all I had to say. I know that I probably opened more questions than I answered, but that is going to be the iterative approach of the data management center until a real head of the center can be found. Thank you.
Thank you.